Alright, today we're going to find derivatives implicitly, and the topic's called implicit differentiation. So we're going to be able to find the derivatives of relations, not just functions. An example of a relation would be x squared plus y squared equals 4. And if you're familiar, this is the equation of a circle centered on the origin with a radius of 2. So implicit differentiation, you're using the power rule like you normally do, the product rule, the quotient rule, whatever the operation implies. However, you're using the chain rule to take derivatives of y terms. So the derivative of x squared is 2x, and the derivative of 2y of y squared is 2y. But the chain rule here would say times the derivative of x with respect to x. Don't worry about that because that's 1. Times the derivative of y with respect to x. Now the key here equals 0, derivative of 4 is 0. The key here is recognizing that we're taking the derivative with respect to x, but we took the derivative of a y term. So we took the power rule, bring the 2 down, then we said, well, what is the derivative of y? Well, it's dy dx. So now, if you recall, this is the noun, so this is what we're trying to solve for. We want dy dx equals. So that's exactly what we're going to do. We're going to solve for dy dx. Subtract 2x from both sides. 2y dy dx equals negative 2x, and divide by 2y. dy dx equals negative x over y. So if we had something like something that's not centered on the origin, like x minus 3 squared minus y plus 4 squared equals 16. Now this is the equation of a hyperbola. Not that that's important, but it's nice to recognize. We could take the derivative of this using the chain rule. 2 times x minus 3 times derivative of x minus 3 minus 2 times y plus 4 times the derivative of y plus 4 equals 0. Okay, just to review what I did there. Chain rule, bring the 2 down, leave the inside alone. Take the derivative of the inside with respect to x. Power rule, bring the exponent down, leave the inside alone, take the derivative of the inside, which I have not done yet. So let's just take the derivatives of the inside now. Derivative of x minus 3 is 1, minus 2 times y plus 4 times the derivative of y plus 4 with respect to x, which is, well, the derivative of y is dy dx, and derivative of 4 is 0. Bring that 0 down. So now we just have to solve for dy dx. So I'm going to subtract that and bring it over there. So negative 2 y plus 4 dy dx equals negative 2 times x minus 3. And now I'm going to divide by negative 2 times y plus 4. So dy dx equals, and the 2's are going to cancel here, x minus 3 over y plus 4. If we had something like an inverse variation hyperbola, x times y equals 4, then I'd have to use the product rule. U equals x, u prime equals 1. V equals y, v prime equals dy dx. So let's plug it into the product rule. So we have u prime v, which is y, plus v prime u, which is x dy dx, equals, that's just the derivative of this. We still have to take derivative of 4, which is 0. Subtract y, and divide by x. So our derivative is negative y over x. Now if we wanted to find equations of tangent lines here, we could rephrase this question to say, find the equation of the tangent line at the order pair 1, 4. Alright, well, that's the derivative here. So this is the m in the point slope formula. y minus y1 equals m times x minus x1. Well, y1 is 4. M, well, we have to plug in this ordered pair to that. So this vertical line here means evaluated at. We're going to evaluate our derivative with the ordered pair 1, 4. And we get dy dx equals negative 4 over 1, which is negative 4. So that's our m and our point slope formula. X minus 1. And just clean it up. Y minus 4 equals negative 4x plus 4. Add 4 to both sides. Y equals negative 4x plus 8. New concept called a normal line. And that is the line perpendicular to the tangent line. So all we have to do is take the negative reciprocal of the slope. So this slope is negative 4 that we found at the ordered pair 1, 4. That's going to help us find the equation of the tangent line. The equation of the normal line, normal slope, is 1/4. So now don't just change it in the tangent lines. You have to redistribute it into the point slope formula. So we're going to use the point slope formula just like we did, but now we just have a different value of m. So y minus y1, which was 4, equals m 1/4 times x minus x1. And just redistribute. Y minus 4 equals 1/4 x minus 1/4, and add 4 to both sides. Y equals 1/4 x. We're adding 16/4 here, so 15/4. So this is the you couldn't even see that. This is the normal line. And this is the tangent line. All at the point 1/4 of the inverse variation hyperbola x times y equals 4. Now graphically what's happening there is we have something that looks like this. We have a hyperbola that looks like this, very rough sketch. The equation of tangent line at the ordered pair 1, 4 looks like this. And the equation of the normal line would be something like that. Normal lines are important for optometry, I guess it is, for eyes, for how the light enters an eyeball. So if you could see this inverse variation hyperbola here, that does model an eyeball a bit. So it's important for like glasses and things like that to make sure the light is entering at a right angle.